Recording is rolling. It is Wednesday, September 14. You guys remember yesterday you were working on the spring scales lab? So go over that in a few minutes. Sure, you guys, what I want you to learn from that one. But before I do, a few other things first. Tomorrow's going to be possibly a weird day. Uh, hmm. I don't know exactly what's going on tomorrow. Have a few plans up in the air because in this particular classroom for the first three classes, periods 1 through 3, there's going to be testing in this room. I don't even know if I'm going to proctor or not. If I don't have to proctor, if I get to be within the classes, I'm going to lug a bunch of equipment around the school and try to get a friction lab done. If I do, well, probably some contingency plan. Right now, since you guys are 6th period, we should actually meet in this classroom, but what we're gonna do, I don't know. We're gonna see. There's a lot of unknowns at this point. Right, and then all right, things up here. Teacher of the Year ballot. So I got this ballot in my room this morning. Right, so now there's a Teacher of the Year, Employee of the Year. Let's just focus here on Teacher of the Year. Let me zoom in here. Right. Well, maybe someday. We're good. We're good with these four. These four right here. Yeah, there's thank you. Thank you for a vote of confidence. So do you guys have some paper on your desk? Like a scrap paper or notes? Go ahead and write down these 4 names. We got Sheritat, Hudkins, Klebs, and Velasquez. Right? Now, every year that I get here's kind of how this works from a school point of view is every teacher gets one of these ballots. Each teacher is supposed to check one of these boxes and then turn it in, and they figure out Teacher of the Year based on that. Okay? But since I don't know how any of these teachers teach their classes, but you guys do because you sit in their classes. You guys have better information than I do. So what I've done every year that I've got one of these, like going back 10 years now, is I always pull my classes. And I also always use this as an opportunity to teach guys about voting systems. So there are different voting systems, for, like, how do you actually operate a democracy? And depending on the system that you go with, you can actually get different outcomes. Now, there are lots of different systems out there, but today I just want to focus on 2. I want to look at one called first past the post and contrast that to a different system that involves ranked choice called specifically instant runoff. We're going to do instant runoff voting. Right? Right. And each of these operates a little bit different way, and they might actually have different outcomes. And so far today, this actually happened to be the case. Depending on which system we went with, there were actually like different winners. Right? This class, I don't know. We're about to find out. Right. So if you guys have on some piece of paper, and I'm not going to pick this up. This is just for you guys to write down. Right. These 4 names written. Right. Now, what I want you guys to do is to think, who on the list would you ideally want to be Teacher of the Year, and put a number 1 next to their name. Okay. So pick your favorite teacher out of those 4. And put a number 1, right? Then think to yourself, well, supposing that person doesn't win, do you have a second favorite? And then find your second favorite and put a 2. And then if you have a third favorite, put a 3. Okay, you guys get that? So let me say it again. So your favorite teacher from this list, put a number 1. Then your second favorite, put number 2. And if you want to rank a number 3, you can rank a number 3. Okay. You guys got that? All right. Now, what you guys effectively just did was to complete what's called a ranked choice ballot, which is not how most voting systems work in the States for like the past 200 years. Most voting systems, what you do is you get a ballot and you just get a bunch of bubbles. And you get to fill in one bubble, right? So you just fill in one bubble and that's it. And you leave the booth, right? But you guys rank your choices, which means that there's actually more information embedded in your ballot, and we can actually make use of that information. Right? Show you guys how. Let's go ahead and go through this process, and you'll see it as this rolls out. Okay? So look at your number 1 choice. You guys see your number 1 choice? Right. We're going to do this just to move this along a little bit. So to pace the class a little better is to do a hand count. Okay. So next to your number 1. Right. How many guys ready to do hand count? How many guys chose the Sheritat as your number 1? Who chose Sheritat as number 1? Number 1. Okay. Oh, okay. That's all right. She's bringing votes all day, but okay. How about Huggins? Huggins number one. Who's got Huggins? We got 1, 2, 3, 4, 5. Okay, so 5 for Huggins. Okay. How do you guys vote for Clubs? Clubs number one. It's got number one for Clubs. Got 1, 2, got 3 on Clubs. Okay. And Velasquez. How many's for Velasquez? We got 1, 2, 3, 4, 5, 6, 7, 8. I'm looking at 8, I think. All right. All right, so you know what, Dan? I'm gonna throw a share tile vote. Here's my Griffin vote. All right, so now everybody has this one vote, right? Yes. All right, so there we go. We ran the election, and there's the results. Right now, question at this point might be who wins the election? So who has the? How about this? Who has the majority votes? Who has the majority? Or is that a trick question? It is a trick question. You guys are on to me, right? Now, why is that a trick? Because what's the definition of majority? Majority means what? It doesn't mean the most votes. It means, yeah, more than 50%, right? Right. Now, whoever has the most, in this case, Velasquez, that's called that's not majority. That's called the what? Starts with a P. Plurality, right? Yeah, guys have it? Right. Right, but nobody has at least 50%. You guys see that? Nobody has at least 50%. Right. So here's where different systems kick into place, and you might get different voters. Right? So this top system, first past the post, is just plurality win, just whoever has the most votes. So if you ran a system with, say, an election with that system, then the winner would be Velasquez in the story. Right? Now, if you sit down and think about this for a little bit, though, this plan immediately, well, it has some cracks in it, some things that don't quite add up. Because if you get a plurality winner that's not a majority winner, well, you're getting a winner that's not representing, say, a majority of voters' interest. Right? And how about this? What if these other 3 teachers are, let's say they all have a similar teaching style, students who could vote for one, they're like, oh yeah, I like Sheriff too. Oh, I like Clubs, they all kind of teach the same. Right? But maybe Velasquez has a completely different style that aligns to like these 8 students that really like Velasquez, but not so much these 3. Right? Well, if these 9 voters up here all got together and said, hey, let's collectively vote, for example, for Hudkins, then it would be 9 to 8, wouldn't it? Right? And then Hudkins would actually win. So what I'm trying to get here is there's something called a spoiler effect, where if there are a bunch of candidates that are kind of similar, and the sort of political analogy is that there are a bunch of candidates who have, say, a very similar platform or on the same part of the political spectrum, all running at the same time, they're actually hurting their interests by voting because they're splitting the vote and making more likely that the opposite of their interest actually ends up winning. Right? So that's called first past the post. Right? But we could definitely do better than that. Right? There are lots of ways to do better. Let's look at just one of many ways called instant runoff. Right? So instant runoff says, okay, well, let's throw out the candidates with the least votes. So in this case, 1, right? And then we'll look at their voters' second preference. You guys remember you ranked your votes? This is where those rankings are going to come in. Right? So let me go ahead and toss out Clubs too. Right? And now we're going to do a revote. Now, in the process of ranked choice voting by instant runoff, you only go to the ballot once. You just fill in the list and then you walk away. You only ever make one trip to the ballot box, right? But there's a process behind the scenes. There's like some machine that does the counting and says, okay, here's number 1s, here's number 2s, right? And they eliminate the lower choice and then automatically defer to the next choices, right? So let's go into the machinery. Right, so where we're going to do this is we're going to do a revote. It's just between Hudkins and Velasquez. So does everybody have a favorite between those 2? Right? You guys think about this? Right, because I'm about to have you guys revote. Now, I know Hudkins is going to get at least 5 votes, and Velasquez is going to get at least 8. I mean, if you voted for them already, you're still voting for them, right? Nothing changes. But if you voted for Chair Todd or Clubs, you guys see how you're going to have to go to your second preference? Guys, all right. So, you guys ready to do? Who's got a question so far? Is there any question? How is this working? I guess this. Right. Okay, pretty straightforward, right? All right. So let's say hand count. All right, for Hudkins. Who's voting for Hudkins now? Got 1, 2, 3, 4, 5, 6. All right, got 6 on Hudkins. Right? And okay, well, yeah, just for formality, let's go and do Velasquez. Velasquez, hand count. Velasquez got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ooh, 11. All right. All right, so in this case, Velasquez wins this class. So I'm doing this with each class. I'm gonna look at the end of the day and see how each class did. But in this case, so Velasquez does end up winning anyway. Right? We've won through either of these systems. But all day today, there have been examples of, actually, maybe we can pull up one here. Yeah, here, let me show you guys my well, one of my earlier classes, right? The initial vote looked something like this, right? No, hold on, that's not a very good example. Where's, here we go, here, this is a great example, right? So here we did this earlier, where it looked like Velasquez was, had the plurality, was in the lead, and we had to do a second preference and then a third preference. And actually clubs ended up coming out on top earlier today because it's ranked choice. But see, what the ranked choice does with the instant runoff is it forces an election until you get a true majority, right? So there's like a majority of students in this case saying, oh yeah, you know, we can get behind this or that teacher, right? You guys got that? All right. So yeah, I've been doing that activity for about 10 years now, and yeah, if you heard about ranked choice in the news, it's like finally starting to get public awareness. So I am happy for that. Mystery Cup challenge. All right, so I got a puzzle for you guys. Puzzle. Okay, got this cup. Right. Interesting looking cup. All right. And oh hey, what's this? Is there a straw hole in the bottom? You guys see that straw hole? Right. And if I flip this upside down, we got another straw here. You see that? Right. Put some water out. Let me get rid of this water. Right. Okay, so I dumped off this side here. Okay. So here's what we know so far about this mystery cup. Okay. Let's look at a cross section. Okay, so cross section looks like something glued together. Right. I see a straw hole looking at the top this way. I flip it upside down. I see a straw hole there. Right. Okay, so that's what we know so far. Right. Now it's been working for me all day. Let's see if I can get this to work. I'm gonna fill this part way up with water. Yeah, this is definitely gonna work. It's gonna work. All right, I think maybe 5 for 5 at this point. Right. Yeah. So you guys see this is filled halfway with water, and it is holding the water. So whatever is going on inside this thing, it is able to hold the water. So there's water filled to that point. Right. Now what I'm gonna do is fill this all the way to the brim, and when I do that, you guys see it starting to leak out the bottom? Hang on, we got a phone call. Let me let's pause this video. Resume. All right, recording is resumed. All right, so it's all right, worked out. Let's take a look here. All right, you guys can see the, let's see, something. All right, so got ourselves a leaky cup. Now, interestingly, what we're about to see, let me go ahead and film this process because it's getting pretty close to the bottom here, is that the water, remember before the water level was halfway and it stayed in the cup perfectly fine? Right. Now the entire cup drains. Okay, let me show you that happened. Bring it back over here, this projection. You guys see there's no water in the cup. Well, there's a little dregs at the bottom, but that doesn't really count, right? Okay. But it's definitely a lot less than it was before. Right. So let's go over this story again. This camera. Okay. So remember, filled up halfway, the water stayed in the cup. Okay. Then I filled it all the way to the brim, and the water leaked out. But it didn't just fall back to the level where it was perfectly happy before. In fact, the entire cup drained. 6 for like little dregs down here at the bottom. Okay. And question for you guys is, well, what's going on between the walls of the cup? Right? How are these? What's going on with these straws? Right? Because I don't have the full picture here. Right? I've just got what you can see from the outside. What's going on the inside of that mechanism? Okay. So I will let you guys think about that for a day, and we'll come back to that another day. Take a look at this slab here. All right, so you guys got a team lab from yesterday. Involved a bunch of spring scales. Right. And here, we're going to go over the solutions, show you guys what I want you to get out of this. So this was really 10 mini labs, right? Checklist here. I think we're doing all right. Okay. So the first one I think was the most straightforward. I wanted you to pick different masses and just weigh them. So you guys had 100 grams, 200 grams, 500 grams, 1,000 grams. Right? Maybe use different masses. Right? And the number was stamped into the lab weight. Right. So now, yeah. All right. So I've got these nice brown scales, which I only had one yesterday, but Okay. If you guys were using the red ones, maybe use the heavier weights. They work better. If you use the little tiny lab weights, maybe you need the blue scales. Okay. But I weigh this, and it's reading about 10 newtons. It's real close to 10 newtons. Let me show that. This guy's here. Let's stop there. About 10 newtons. Okay. Okay. So that's the 1,000 grams stamped in. That's 1 kilogram. Weighs about 10 newtons. I'll tell you guys more precisely, it's actually 9.8, but the scales aren't like super accurate anyway. So more often than not, I might round that to 10. Right? Guys, if the 1,000 grams has a weight, like a gravity force pulling down of 10 newtons, what do you think 100 grams was? 1 newton. What do you think 200 grams was? 2. Right? And then 500 grams would have been like 5 newtons, right? Or maybe you're looking straight on your lab paper because you have that data recorded, right? Let me do a little side thought here. Right? This is 1 kilogram, right? 1 kilogram. If I take this into deep space, is this still 1 kilogram worth of mass? Yeah, it sure is, right? Which means 1 kilogram worth of material. It also represents 1 kilogram worth of inertia, which means if you push on it with a certain force, right, the more mass it has, the less it wants to accelerate, which relates to Newton's second law of motion, right? If you put a force on a mass, cause acceleration, the greater the mass, the less it will accelerate, right? And that would still be true even in deep space if there's no gravity force on it, right? But I know that here at the surface of Earth, this is being pulled down with 10 newtons of gravity force, and in deep space, that number would be 0, right? Because it'd just be floating around. Right? So it has mass, but not weight in space. Right? So let's graph this thing. Right, so I had mass of 100 grams, 200 grams, 500 grams, 1,000 grams. So mass is in grams, and the force is in newtons. It went 1 newton, 2 newton, 5 newton, 10 newton, right? So if you plot those points, right, here's ideally what your graph should have been. It should have been just a direct relationship, just like that. Just like, right? You guys got that? And this line has an equation. And the equation goes, the force, like the gravity force pulling down, and therefore the tension force to keep it in equilibrium, is equal to, I'm going to say mg, right? Where m is the independent variable. Well, in this case, measuring grams, so it's like mass in grams. Okay? And the slope is like the gravity field of the planet, which is, hey, that's about 10 meters per second squared, right? That's why if you have 1 kilogram times 10 meters per second squared, you get 10 newtons of gravity force. Look at that, right? Is that? Right. And I will actually pretty commonly in this class use this notation going forward, mg, to represent the weight of some object, which was like the downward pulling gravity force. You guys remember this packet from very first day of school? You guys walked in, this was on your desk? Okay. So here's a bunch of variables, what it means, the units, and right here, m times g. Whenever you guys see me write mg, I'm multiplying 2 variables together, mass and gravity field, to represent the weight of an object measured in newtons. All right, guys got that? All right, so next one, number 2. Can you distribute the weight? So where's, okay, lab mass, a couple of spring scales. Okay. Now, if this weighs, let's say it's a 1 kilogram mass, which weighs like 10 newtons. Okay. What if I have it balanced evenly, like half and half? Shouldn't it be 5 newtons and 5 newtons? Right? You guys probably saw this yesterday. So like 5 newtons on the left side, 5 newtons on the right side, for a total force of 10 newtons. Okay, 5 and 5 is 10. But could I maybe redistribute it to like put more force on one and right? So what if I shift these a little bit so that one of these is carrying, let's say 7 newtons. Now what is the other one carrying? 3. So they still add up to 10, right? What if I put 9 newtons on one side? What's the other one? 1. Yes. Okay. So you guys see that pattern, right? What if let's do one more. What if I put 2 newtons on one side? What's the other one? 8. All right. So they always add up to 10, right? And then I had you guys graph what is the left force versus the right force. So you could go up to 10. This would be in newtons. Up to 10. This is also in newtons. Go up to 10. Okay. So 5 was actually a coordinate because it could be 5 and 5. It could be 7 and 3. It could be 9 and 1. It could be 2 and 8. Right? And if you connect all the points, zoop, that is ideally what that graph should look like, right? Just a straight line with a negative slope. Right? Just like that. Okay. now is actually a pretty good point to introduce another concept you guys called free body diagram. Okay. So free body diagram. We're going to do a bunch of these over the next few weeks. This is a really important concept in physics, oftentimes abbreviated FBD, free body diagram. What this is you just label all the forces on an object. Or maybe like on a system, or depending on what you're defining. Right? So in this case, let's do it for this one. Had this lab mass. Okay, put a big old dot where its center mass is, like right there. Okay, right. So we look at that object, and I'm thinking that here I'm following this right here. There are 3 forces on this right here to hold it in equilibrium. 3 forces. Okay, there's its weight pulling down. So that would be I might say it like this: mg equals 10 newtons, right? The weight is 10 newtons pulling down. Okay? And then there were a couple spring scales pulling up. Maybe it was like something like this, for example. Maybe the force on the left side could have been 7 newtons, and the force on the right side could have been 3 newtons. Make that a little bolder, see a little better. There's a 3 Newton force, here's a 7 Newton force, and here's a 10 Newton force. Okay, guys see that? 10 down, and then 7 and 3 up. Okay, so you guys see 7 plus 3 minus 10 zeroes out. That's to say that if you're holding it in equilibrium, then there would be 0 net force. Guess that? That's actually what the definition of equilibrium is. But later on, we'll also say that torque also goes to 0. But for now, the next few weeks we'll do equilibrium. We're going to say the sum of the forces is equal to 0 newtons. So this is the sum of forces is 0 newtons. Okay. You guys got that? All right. In this particular scenario, I might say like in the y direction, because that would be true, right? Okay. Now, remember, let's tie this back to Newton's second law of motion again, right? Guys, if there's 0 net force, that means that the system is also not doing what? How is it not moving? Accelerating, right? Guys, if there's 0 net force, there's going to be 0 acceleration, right? Guys, does Newton's second law of motion say anything about velocity? It does not, right? So can something be moving at constant velocity and still be in equilibrium? Yeah. So you could, in fact, you could be moving really fast and still be in equilibrium. In fact, if you guys are going up I-95 at 70 miles an hour cruise control, you can still be in equilibrium. Your net force could be 0. You might have 0 acceleration. Okay. All right. Next one. Now let's take this and let's take it 2-dimensional. So you start to spread this out to a Y pattern and get closer and closer to a T. Right. Now this one right here is pretty critical. It's going to show up a bunch in the next few weeks. Right. So pay close attention. Okay. See how I put like a vertical dashed line here, and then it said measure an angle with respect to that. So it starts out 0 degrees, just straight vertical. But then as you make it closer and closer to a T, if you did have a perfect T, that angle would approach 90 degrees. Is that? So I'm going to put some angles on here. Let's say 30 degrees, 60 degrees, and let's go ahead. A pretty big one. Okay. All right. Thank you. Okay. And I know that this was a mass of 1 kilogram. Oh, yeah, thank you. 1 kilogram. Okay. And if that's true, here, guys, on here. Okay, so what would this bottom scale be reading for a 1 kilogram mass? How many newtons? You guys say 10 newtons? 10 newtons of force? Right. Let me go down to this. Oh, and wouldn't that be true for regardless of the configuration? The bottom scale is always reading the same value, the bottom scale. So I'm going to put 10 newtons on the bottom spring. It's just 10 newtons all the way down. Okay. Now the top springs is a different story. Right, so I have a small confined space right here, so I'm just gonna cut out the bottom one, and you guys did that yesterday, so you guys gathered that in turn plugins. I'm just gonna do the top 2. So if I hook these like this, There we go. All right, lift it straight up. Yeah, so all right, right now I'm reading 5 newtons at 5 newtons. Let's say I spread this out so that with respect to the vertical, there's like a 30-degree angle there, maybe 60 degrees between the two, right? And actually it jumps up a little bit. Right now I'm reading about 6 newtons. So I get to about like 6 newtons at that level. That's interesting. Or so each top spring, it was 5 newtons. Right? Spread them out a little bit, it actually goes up a little bit. Interesting. Right? Hey, what if I make like a perfect Y shape? Right? What if I take this angle to the vertical and take it all the way to 60 degrees? Now, let me put a little star next to this one because this one's going to be a special scenario. I'm going to do a whole free body diagram with this. Right? Now that exactly maxes out these Brown scales to 10 newtons. Right? I'm looking at it right here. It's going like well, that's the grams. Here's just the newton side. Right? It's going like 10 newtons. 10 newtons. Right? Right? And if I go beyond that, well, I would really need to pick up the red or the white scales because it like overextends the brown ones. They beyond that. But just to throw a number in here, maybe something like that. For example. Okay. Right. Now let's go to the starred row where this angle to the vertical is 60 degrees. Right. Where hey, it looks like each top spring was reading exactly what the weight was pulling down. That's kind of interesting. I wonder what the free body diagram looks like for that particular scenario. Okay. So let's do that. Let's make a free body diagram for that scenario. I'm going to introduce a Cartesian plane, or this doesn't, there's no actual lines floating around in the real world, but we're going to use these as reference lines, right? Okay. And I'm going to look at this point where all 3 scales sort of come together, like right here, where they all come together, right? And draw some force vectors. That's what free body diagram is. Right? We're just drawing a bunch of force vectors. Right? Let me get this spot right. Right there. Okay. I know that the weight was pulling down with really close to 10 newtons. So I'll just call it 10 newtons. Right? 10 newtons down. Okay. And let's say that pulling up to the right, this is 60 degrees to the vertical, which is right here. Bam. Pull that way. When hey, I got the measured empirical value, it was 10 newtons, wasn't it? 10 newtons that way. And let's also go up to the left. Bam, 60 degrees that way. So we're looking at 10 newtons that way. Right? Now, I'm going to change the story up a little bit. Let's get rid of those dashed Cartesian lines and just focus on the 3 vectors. You guys see the 3 vectors? Right. Let's put this story into place. Suppose you and a couple of friends get together and say, hey, let's have a 3-way tug of war. So you tie some ropes together, make a big old knot in the middle, right? And you pull 3 separate ways, like something from Good, Bad, and the Ugly. Right? You guys see this? Right? Right. Now, could you imagine? Here, I forgot to go. Let's do some numbers, guys. If this angle is 60 degrees, that's what establishes, right? 60 degrees from the vertical. What's the total angle between these two guys? 120. What's this angle right here? 120. And what's this angle? 120. Is this like a perfect Y shape? Like it's completely symmetrical. I could like turn this around and right. You guys get that? Okay. All right. So it doesn't matter necessarily that this force pulling down happens to be a weight force, and these two happen to be spring forces. Right? Just any kind of force. This is completely symmetrical. You can like rotate it around. Okay. Oh, okay. So from that point of view, it totally does make sense then. That these would each be 10 newtons. 10, 10, and 10 would exactly balance out. Okay, okay. Now let's put the Cartesian system back in place. Right. So those dashed lines are back there now. You guys see the dashed line? Okay. Right. And let's do some component analysis. You guys remember all the SOHCAHTOA? You think SOHCAHTOA is about to come back? I did some trigonometry with you guys before we ever did any kinematic motion. Then it came back with projectiles, and now it's back again with forces. So the force pulling up to the left, I want to be able to quantify how much up and how much to the left. So I'm going to break it into components. Notice I'm dashing these components, so I'm not double representing the force vectors. And how about this guy up here, pulling up to the right? Well, how much to the right and how much up is this guy pulling? Right, those components. You guys see those components? Right. What could possibly be helpful? Maybe not 100% necessary, but guys, what's that angle right there? Is that 30 degrees? Okay. How about this angle over here? Is that 60 degrees? Got myself a nice little right triangle going on. Okay. Right. And if you know this hypotenuse is 10 newtons in magnitude, 10 newtons, You know that these angles. Can you guys solve for? Let's start with this one right here. How many newtons strictly up is this? How would you find out? Is that 10 newtons times what?
I'm saying like cosine.
Cosine of which angle? 60 degrees, because it's adjacent to the 60 degrees, isn't it? That's why it's cosine. Okay. If you try this on your calculator, oh, I got it right here. 10 cosine 60 degrees. 5 exactly. Look at that. 5 exactly. 5 newtons. Okay. Hey, could you have done this instead? Could you have gone 10 newtons times sine of 30 degrees and gotten the exact same thing? Right? So you can play off either angle. Right? Whether you do opposite of 30 or adjacent to the 60. Right? Either way, you're going to get 5 newtons. Right? For that. 10 sine 30. Yeah, 5. Also 5. Look at that. Right? So we got this thing pulling strictly 5 units. Hey, I wonder how much to the right it's pulling exactly. Yeah, cosine of 30, right? So 10 newtons times cosine of 30 degrees. And that is 8.66 newtons to the right. Okay, let me pause this again. Pause. And recording is resumed. Right, so 10 newtons at this 60-degree angle from the vertical. That's the same thing as saying it's pulling strictly up with 5 newtons and strictly to the right with 8.66 newtons. Okay, guys got that? Hey, because this whole thing is symmetrical, do you think it's the same story over here? Same type triangle? Think it's also pulling up with 5 newtons, of course, and left with 8.66 newtons? Kind of makes sense, right? Is that? Right. Now, remember, there's only 3 forces here, right? The weight and the 2 spring scales. But I split the spring scales into components, and I've circled the 5 components that are exactly aligned to the Cartesian system, right? And one was already along the Cartesian system, but the weight is, right? So remember the conditions for equilibrium? Right? We're saying the sum of the forces is equal to 0 newtons. We wrote that just a few minutes ago. Right? I'm going to get a little bit more granular. Let's say the sum of the forces in the x direction and in the y direction. Right? Once you introduce a Cartesian system, that'd be true for equilibrium, right? The sum of the forces. Okay. Guys, if you're just holding something at rest, it's not moving, that would be equilibrium, wouldn't it? So this should be equilibrium. Do you guys see x direction? 8.66 minus 8.66 does in fact zero out. And you guys further see that 5 plus 5 minus 10 also zeroes out in the y direction, right? The 5 up balances with the 10 down. Okay, so, right? Now, I had you guys yesterday here. The 60-degree angle is only one of many angles that you guys did, right? It's that angle right there, but you guys probably did a few other angles too, right? So do you think you could change this angle to whatever, right? And the fact that it's supporting 10 newtons of weight, do you think that you're always going to have 5 and 5 newtons for these 2 components? Yeah, you'd have to. There's no other way. It has to be 5 and 5, or at least they have to add up to 10, right? Maybe if you did some weird configuration where it wasn't super symmetrical, you might get like 6 and 4, but right? Yeah, they do have to add up to 10 to satisfy this condition. And if it's all symmetrical and balanced, it'd be 5 and 5. Now that's actually going to help you out with the question coming up here. So let's do this graph and then answer these boxes down here. So draw force of each top spring versus the angle. Well, I know at 0 degrees angle, it was 5 newtons. These are all in newtons. Right. Throw on a 5 and a 10. So 0 degrees was 5. Got a point right there. At 30 degrees, it bumped up a little bit. It was like almost 6. At 60 degrees, it exactly matched the weight, which I just did the whole free body diagram, guys. So 60 degrees, it was 10 newtons, right? And if you went beyond that, it just got like crazy big at some point, right? So the ideal answer for this graph should have looked like that. Do you guys get something like that? Something like that about? Right. Right. Now, these questions right here, as this angle with respect to the vertical approaches 90 degrees, another way of saying that is as you get this configuration closer and closer to a perfect T, what do you think the force in each top spring approaches? What does this graph kind of tend towards? How about this? Let's answer the second question first, right? Because maybe that will give some kind of insight. Can this angle actually ever physically reach 90 degrees? Let's say, can you ever make a perfect T? Can you make a perfect T? Wait a minute. Didn't you guys just tell me a minute ago that there has to be some vertical component like 5 and 5 to balance out this 10 down to satisfy this condition for equilibrium, right? And if there has to be some upward component, a perfect T would never even have that upward component, right? So can you have a perfect T? No, that's physically impossible. Right? So the answer to this question is no. Right? So go back to the question leading into that. As that angle does approach 90 degrees, which you can never physically reach, what do you think this force is heading towards? Were you guys thinking infinity? Infinity, right? Hey, I bet this graph has a vertical asymptote right here at this angle. Let's take a vertical asymptote, up like that. You guys got that? Everybody? All right, you guys ready for the chain game? You guys ever play Barrel of Monkeys? Get a barrel full of plastic monkeys, you chain them all, that basically this configuration. Hey, if you were one of those monkeys, what would be easier? Would it be easier to be a monkey near the top, holding up all your monkey friends, or be like the monkey at the bottom, just holding up yourself? I'd rather be at the bottom too, right? And that's where we're kind of going with this one. So let's throw in some values: 1 kilogram, 1 kilogram, 1 kilogram, right? Yeah, maybe you guys did something pretty similar to that yesterday. Remember, each of these kilogram masses weighs about 10 newtons of gravity force, right? So the top scale, in my native example, would read about how many newtons? About 30, right? How about the bottom scale? Just these 10? What about the middle scale? What's this guy read? I think 20 newtons? Like 20 newtons? Okay, so that's interesting. Right. Oh, how about this? You go to an old warehouse and you open up the door, right? You see a heavy metal chain just hanging there. It's been hanging there since the 1940s, just like rusting over, right? And you're, hey, I wonder which link in this heavy metal chain is most likely to break first. What do you guys think? One near the top or one near the bottom? Top, yeah, because it has to hold all those links beneath it. They each have their own weights, right? Has to hold more force at the top, more likely to break. Let's do a variation on that. So here's the next one. What if you just slip another spring scale in the middle? We'll make the same masses. 1 kilogram, 1 kilogram, 1 kilogram, right? And well, I know the top one is going to still read 30 newtons. That's not going to change. The bottom one's still going to read 10 newtons. That doesn't change. Okay. But now, the crux of this one is what's going on with the middle two. Here, I'll narrow it down for you guys. Is it going to be? I remember with just one, it was 20, right? That one. Right. So is it going to be 20-20 or is it going to be 10-10? What do you guys think? 10-10. Yeah, that's what you guys saw yesterday, right? The force splits. It's going to go 10-10. Okay? You guys all right with that? All right. Ever good so far? Who's got any question? Any question? All right. So to the back. Elevator weight. How do you guys accelerate this up and down? Okay. Now, let's get this on here. You guys ever step in an elevator? Elevator starts to move. You feel that weird feeling in your stomach, like, whoa, this whole floor is moving. You guys feel that? Okay. And then the elevator gets going at constant speed. Now, constant speed, guys, what's the acceleration associated with constant speed? 0 acceleration. So while you're going up constant speed in the elevator, you're not actually accelerating. You should feel a lot like you feel in this room. But then the elevator slows to a stop, and then you feel weird again, like, whoa, feels like something's moving, right? And I'm most interested in those parts where it's changing its motion, because that's acceleration. And remember how you get accelerations. Accelerations are caused by forces, right? Acting on masses, right? So maybe there's a force from your hand, like moving this spring scale up and down, right? And as it bounces up and down, probably need the red one for this one. Grab a red spring scale. Right, there we go. Red spring scale is better for this bouncy one. Right. Here, I'll do simulation from the side. So you can't really see it on the camera otherwise, but it was like bouncing like kind of oscillating up and down, right? Now, one way to make it accelerate up is to start from rest and just pull it up faster and faster. Maybe that's the most obvious way to accelerate it up. Pull it faster, right? That's like if you step in an elevator and you're on the ground floor and it starts to move upward, right? Now in that case, does the force rating go up or down? It does go up. So I'm going to say increase. Yeah. If you're standing on a bathroom scale in an elevator, you would be briefly heavier than your usual weight. Okay. There is another way to make it also accelerate up that's not as obvious, but it involves actually moving the whole system down. Because if it's moving down, has a downward velocity, how do you also make it accelerate up? It's moving down doing what? Slow into a stop. So if I bring this down, isn't the force rating gonna increase just briefly while it's slow to stop? Right? So that's also that. Right? How about the other one? Accelerating down. Now, maybe the most obvious way to make accelerate down is to let it go down faster and faster. In fact, an extreme example of this would be pure free fall. What if I just let this go? And just like edge of a cliff, just like it's all just like falling off the edge of a cliff, right? Or you step in an elevator, so it's and cuts the cable, and it's like just like free fall all the way down. Guys, what's this gonna read in free fall? 0. So that's an extreme version of like accelerating down. In general, shouldn't the force decrease? Right? And finally for this one, there is a second way to also make it accelerate down that's maybe not as obvious, but it's probably easier to read. And that involves moving this up and doing what with it? To stop. Yeah, move it up and bring it to a stop. And then it will very briefly, I can't quite get this guy on camera. Okay. It will very briefly, though, decrease in force, which is also an example of that. Okay, is that? Right, next one. What if you tie with a string and then start, say put a force on this top one to accelerate it back and forth. Right? This is actually a variation on this, but got the four questions, right? Okay. So when the top spring is moving left and speeding up, that's to say that there's a net force to the left and an acceleration to the left. What's going to happen to the tension of the string? Increase or decrease? Increase. Right. What if you, next scenario, move the top spring to the left and slow it down? Does that put a little bit of slack in the tension? Yeah, that would actually decrease the force, wouldn't it? Force spring is going to go down a little bit. Okay. All right, so as you're moving it to the left but slowing down, there might be your own force to the left, but there's other forces like this weight over here, tension, maybe some friction. So the net force is actually to the right. So there's acceleration to the right. Okay, that's the second scenario. Third scenario, when the top spring is moving to the right and speeding up. Oh, I could think of an extreme example. An extreme example is that you just let it go. Isn't that when you definitely move to the right, speeding up? Right? In that case, wouldn't the tension pretty well go close to 0? Right? So that would definitely be a decreasing force situation. Right? And in the last scenario, suppose you move it to the right and then bring it to a stop. While you're bringing it to a stop, what happens to the tension in the string? It's going to jump up real briefly. Yeah, that would be an increasing force. Okay? Right. So if you got all 4 of those questions right, goes for each of the scenarios, goes increase, decrease, decrease, increase. Okay? Right. Guys got that? All right. And friction. Right. This is as far as I've been. Here, we're going to do friction real fast. Right. So I'm going to do a more extensive version of this lab, well, sometime in the near future. But I had you guys lift the mass. So 1 kilogram weighs, the lifting force is 10 newtons. Right? And then drag it across the paper, right? And I'm reading on the spring scale about 3 newtons. If I drag it at constant velocity, which is what it says here to constant speed, it's about 3 newtons. Hey, that 3 newtons drag force, do you think that has anything to do with these 2 materials, like this metal and this paper? Do you think if I replace this regular paper with sandpaper, it'd take more force to drag it? Do you think if I replace it with really slippery wax paper, probably not as much force? Yes. Interesting, right? Do you guys think that the ratio of these 2 numbers, 3 newtons to 10 newtons, is an important value in physics?
Yes.
It is, because that's the leading question. Right, so that's called the coefficient of friction. Actually, technically, it's coefficient of friction is the friction force divided by what's called the normal force. Right. Now here's where I've been kind of running out of time today, but we got to sketch up. I'll get you guys exactly up to where I got all my other classes. Right. I got a lab mass here. It's got this little Captain Hook going on. Got a spring scale right here. Right. And suppose I'm pulling this to the right at constant velocity. let's do a free body diagram. FBD, free body diagram. We did a couple of those earlier today, right? Now, guys, there's 4 forces acting on this mass as you're pulling it constant velocity. There's 4 forces, right? You know what? We got just a few seconds to the bell, so and that's where I've been leaving all my class today. So I'm gonna leave that for you guys to think about that overnight. There's 4 forces acting on that, and we'll pick up sometime in the future. All right. So wrap on today.